With all the redefinitions of certain parameters of your life at this point, it may be confusing to even visualize what is what anymore. What is up, what is down, what is left, what is right, what is even moving forward anymore. Well, today I think it's important that we take a step back, maybe regress, some might say. That's right. Today we're talking about linear and nonlinear regression. Hit that intro. No? No intro. Well, fine, you're used to it at this point. Anyway, let's go ahead and jump into some of this linear and nonlinear regression. So, we're going to do this using the Antoine equation today. And what is the Antoine equation? Let's go ahead and define that again. Antoine equation. And what that is, in its most standard form, log base 10 of the saturation vapor pressure of a substance is going to be equal to some parameter A minus some parameter B over T plus C, where T is temperature. Alright. So we've seen this equation before, let's kind of mess with it again. This time we're going to try and use that as a model to fit our data. And we are given data here in this file, this CSV file, so generously provided experimentally by the University of Cincinnati. How nice is that? So kind of them. So, now that we kind of have all of our data here, we want to perform some regression onto it. And what really does that mean? I'll show you. What that means is that if I were to plot all of temperature versus pressure graph, what I would do is I would have all of my points kind of splayed out here. Let's say I have points looking like that. And then I want to draw some sort of model to fit them. So some sort of curve, potentially, or even some sort of line. Well, first let's talk about nonlinear regression. By which we are going to perform a sum square error. Now, what exactly is this sum square error? Well, for each point, we're going to draw a line from it to our model. Our model is in red here. And then our experimental data are these little dots. Experimental data here. Now, this pink here is our error. So we're going to calculate our error by determining the distance between our experimental data and our model in the y direction. In this case, that's the pressure direction. Well, that is all fine and dandy. And we can go ahead and we can do that for literally every single point here. And we would draw error bars for all of those. And once we find that error is equal to, basically, our experimental pressure minus our theoretical pressure. And we can just go ahead and sum them up. Hence, sum square error. Now, once we've kind of summed them up, you may notice that the error above the bar, this positive error up here, and this negative error down here, is going to cancel each other out. For example, if this error was, let's say, 2 and this error was 3, I'm just making up numbers here, then you would come out with a -1 error, when in all actuality you should have a total of like 5 error there, right? So to account for this discrepancy, we are just going to square our error term there. So sum of the squared error. And our goal then is to minimize this function. And that is going to take place through some calculus. I'm not going to define all of that here. All I'm going to say is that we are minimizing it. But this equation in pink here is the equation for sum squared error. And this is how we can go ahead and perform our nonlinear regression for our data here. So let's go ahead and jump into Google Colab and do that. I'm going to leave our equation on screen here. Wonderful. Okay. Nice. Oh, now it's going to block me out. Okay. So there is our equation. Now, to go ahead and minimize this function, we are actually going to use a function from the SciPy optimize library called minimize, aptly. We also need our NumPy library. Oh, I don't know what that is. Let's go ahead and import that first. And then finally, we just need to import some sort of visual function to visually check our math here. So to do this, we will import a plotly subplots make subplots. Awesome. So once we've got all of that imported, the next important thing to kind of do here is to grab our data. So let's first get it. And here is our data. On the left you can see we have our temperature values, and on the right are our pressure values. So let's go ahead and grab that. And then we need to define some sort of variable as the vector quantity of our data here. So let's do that. This is going to read our text here. We called it is called the water vapor pressure dot CSV. So now that we've grabbed it, let's go ahead and split our data into its two components, temperature first, and then experimental saturation vapor pressures second. And transpose it. Perfect. Cool. Now that we have all of our data extracted, it's time to go ahead and define a sum squared error function. And to import, we're going to import our Antoine coefficients, as that is what we are attempting to find with our minimize function here. So our vector is going to be equal to A, B, and C. And then we need our theoretical pressures. Well, this is going to be determined by our model, which is the Antoine equation here. So let's go ahead and throw in the Antoine equation. And then finally, we're returning the sum of our square errors. So the sum of our errors squared. And remember, our errors, as this equation states, is very clearly our experimental pressure minus our theoretical pressure. Awesome. So now we've defined that function, I think the next important thing to do would be to minimize it. So let's minimize our function, and it is going to input some initial guesses. I have gone ahead and pre-gamed these guesses. which is how I am coming up with them here. Let's see. Sum squared error. Little syntax error there. Nothing we can't fix. Awesome. So, we did get a little bit of an overflow warning. Likely this is just due to slightly invalid initial guesses. So, let's see. Let's kind of mess around with our initial guesses just a tiny bit. Okay, and there we go. That gives us some better pressures here. Or, sorry, better Antoine coefficients here in our array. Now that we've exported our minimized function, and we have minimized our sum squared error, I think it's important that we kind of see how well our coefficients actually fit into our model function on a graph. So let's go ahead and make a plot here. And we'll add to it first our experimental data. Temperature is our x variable. Experimental pressure is our y variable. And our mode is just going to be points here. So let's actually look at that first. Move our equations out of the way here. I'll just minimize that for now. Awesome. So here we have all of our points actually plotted. And as you can see, this is definitely some sort of logarithmic curve, which works by our model. So let's go ahead and add in our model. However, to add in our model, it looks like we're going to actually have to define some sort of Antoine equation function with which to import our guessed or our estimated values for its coefficients. So let's go ahead and define that function here. Antoine equation, I'll import as a vector. However, you could do this a multitude of ways. So we'll just go ahead and say A, B, and C is our vector. And what do we want to return? We want to return our theoretical pressures. So this will just be this, 10 to the A minus B over T plus C. Go ahead and run that. So then we can throw in that equation as our y variable there. And its input will be our minimized sum squared error. So we can go ahead and say Antoine equation with its minimized sum squared error. So let's go ahead and set this equal to a variable. I'm going to call it ABC. And all that means is that's our sum squared error. Our mode then is going to be equal to lines. And let's go ahead and plot it. Oh, I need to run this. Perfect. So as you can see, our model does do a fairly decent job of connecting to our points. If I'm to zoom in here, you can see that it's definitely going to be off a little bit, but all in all, our nonlinear regression was performed fairly successfully. So that's kind of how to perform our nonlinear regression. However, with the Antoine equation, we are granted the special capability of making it a linear regression. And you're like, that doesn't make sense. It's a logarithmic equation. How could we possibly do that? Well, we're going to mess with some matrices. Let me show you. So we're going to have to go ahead and go right back to the drawing board here in order to do this. So let's next do our linear regression. First, let's go ahead and again write our equation. I'm just going to call our saturation vapor pressure P this time. Awesome. So the first thing I'm going to do, I'm going to multiply the entire equation by this term on the bottom here, this T plus C. So when I do that, I will end with this. Now, here I'm going to define a new variable d as being equal to AC minus b. Now when I do this, it will eradicate our b term. However, we will be left with 3 unknowns in our equation then. Still. Awesome. So, let's go ahead and do this. And I'm also going to move this over to the other side of the equation. Now, this form is going to be the form we're going to throw into our matrices. To do this, we must first construct a design matrix, X. So I'll call this design matrix X. And it's going to be a 3-column matrix multiplied by the rows, which will be the number of temperature values we're given. We'll call that N, and that won't particularly matter to our equation here, because we want to be able to do this for any amount of temperatures and pressures given. So, in our design matrix, we are going to have it multiplied by our variable matrix, and our variable matrix is then going to give us our y here. And this is why we're kind of calling this a linear regression. We're just multiplying it by our variables to give us y. Y is then going to be our T log 10 of pressures. And again, because these are given to us, that makes that easier to solve. And it will be how many ever times we have that. Our variables are going to be A, C, and D. And then our design matrix then, well, A is multiplied by T here. So T will go ahead and be our first column. Next, I'm going to throw in our C term. C was next in here. And that is negative log 10 P. And then finally, our D term is 1s, so we are just going to do 1s. And again, this will be however many terms we are given. Now, how do we solve this set of matrices here? Well, we're going to do a little bit of linear algebra here. So if X was a square matrix per se, then we could just take its inverse, and then it would be equal to 1. And we would then have a function of y that is going to be equal to our variables. So to make X a square matrix, what we are going to do is multiply it by its transpose. So I'll call that X transpose times X. Okay. And then I said I can take the inverse of that, and it's going to be equal to 1. Similarly, I guess I'm going to have to do that on the other side as well. So, X transpose times X times its inverse times X transpose times our y function here will be equal to our variables. So let's go ahead and attempt to code this out here with the data we've been given experimentally. So let's jump right into this. We're going to need our design matrix here, and again we called that X. So we'll just do an NP columns, and temperature will be the first column. Then we have, oh, let me pin our equations here to the front so we can see what we're doing. Temperature, well, that didn't work in the slightest. Temperature is our first one, negative log 10p, so I'll say negative np dot log 10p, and this will be our p experimental. And then finally we'll do np1s like, let's just say t. Let's see, NumPy has no attribute c. There we go. Slight syntax error in my columns function there. Now we have our design matrix. Now let's go ahead and pull our linear algebra together in order to solve this. Okay. So we are just going to do X dot transpose and multiply that by X, and this will be the inverse, np dot lin algebra dot inverse here of this function. Then we'll multiply that by X transpose, that should be lowercase x, X transpose, and we'll multiply that by Y. What is Y? We said it was temperature multiplied by np dot log 10 of our experimental pressure. Right? I think that should go ahead and solve here. And what is this solving for? Well, we said it's going to solve for our A, our C, and our D. So let's go ahead and define that there. Awesome. Now we have our A, C, and D. I think next, all we kind of need to do here is throw in our, or find, rather, our B function. So B is going to be equal to, we said D is equal to AC minus B. So B, by an algebraic manipulation here, I'll write this in red just so it's differentiated, B plus D is going to be equal to AC, therefore B is equal to AC minus D. AC minus D. And we need to multiply these, I should say. And now we have a B function in there as well. Well, there's only one way to see if our linear regression actually worked, and that's to throw it on this plot here. So plot.add underscore scatter, and let's see. Okay, we need our X to be temperature again. We need our Y is going to be our Antoine equation, and it inputs them as a vector. So we need actually, the easiest way for me to do this is just going to be to define a second Antoine equation function that takes inputs as A, B, and C. So I'll call it Antoine Equation 2 because I'm out of variable names for the day. A, B, C will be its inputs, and we will just return then 10 to the power A minus B over T plus C. Which means all of these kind of blocks here are going to need to be defined above our plot. So let's throw a piece of code in, do that, run it. And now Antoine Equation 2 inputs are going to be A, B, and C. And that should be good. Our mode then is going to be equal to lines again. And you can see on this graph we have almost a direct overlap between our two regressions here. Look at that. You can see our linear regression is slightly off of our nonlinear regression. However, they are still, when looking at it from a giant view, almost indistinguishable. At lower values, our linear regression is going to be more absolute, and this is due to the logarithmic nature of our function here. Okay, in this video we performed 2 linear regressions using Python's Colaboratory. One was linear for the Antoine equation, and one was nonlinear. I hope this helped. Peace.